So deep learning today is crucial for computer science. It can resolve unprecedented problems. Oh, that's nice. In any field that you can think about, automotive, healthcare, natural language processing. And in particular, we will focus here on healthcare. In healthcare, deep learning is used for automatic diagnosis, especially from images like X and CT scans. And it is used to help physicians in make diagnosis, not to substitute the physician. And in particular, this European project called DeepHealth, this one, was started to prepare a unified framework for deep learning on big data architectures and on HPC. And the second question is, yes, deep learning is important, but why putting it on Kubernetes? Reasons are many. Kubernetes is everywhere. All cloud vendors use Kubernetes now. And since it is widely used, basically, if you need an application, you can find a Kubernetes way to deploy it. So this is an important point. It's reliable. It has been used in production for years on huge scales, so it is resilient. And it's also extensible. You need your API, you can build it. So you're not forced to stick with the product. So then why don't only use Kubernetes? Kubernetes is a very beautiful platform for orchestration, but it lacks some important features when you deal with data. Data, especially medical data, are private. And if you host multiple hospitals, multiple entities that bring their data to you, you need to ensure multi-tenancy. I see my data, you see your data, but I don't see others' data. Multi-tenancy in Kubernetes can be done, but it's not easy to do it with raw Kubernetes. And this will be what Dario will explain you later. Second, Kubernetes is not transparent in terms of performances. You have bottlenecks on the network, bottlenecks on the storage, and when you need to go at high scales with deep learning, you need performances. Otherwise, your workloads can take weeks, months, years. And finally, Kubernetes is too complex because asking a physician to learn Kubernetes is like asking a computer scientist to operate on a patient, basically. They will never do it. So this is where we came up with this very linear and obvious architecture that you see here, that I will explain during this talk. We basically had many layers on stack. We have the physical layer, the gray one, which is cloud and HPC. So virtual machines and bare metal. We need virtual machines for hosting services, for on-demand usage. We need bare metal for performances. So instead of trying to build a hybrid, we put them together and use the software to make them transparent to the users, basically. Then we put Kubernetes on top of VMs, and we put a software platform that allows people to use all the stack. And basically, we thought about two kinds of users. The computer scientists that want to do things quickly, flexibly, without clicking with the mouse, but writing code and using command line interface. And this is the blue access path, so that one that I will describe to you now. And then for people not from the IT field, but more data scientists coming from mathematics, coming from domain experts or physicians in this case, we prepared a Jupyter notebook-based access path that makes basically the same things in a slightly less flexible way, but slightly much more user-friendly access to the platform. The idea behind all the workload is using hybrid workflows. Hybrid workflows, by definition, are modular applications in which any module can run on a separate platform, the platform which is best suitable for the thing it has to do. And such platforms can be heterogeneous, so cloud, HPC, one piece on cloud, one piece on HPC, and independent. So we don't force platforms to have one single way shared among all of them to communicate. For example, we do not pretend they have the same file system, the same storage object store, because HPC and cloud are very different worlds, and pretending that they use the same technology practically always ends up in limiting one of them. This falls under the curtain of the Across European project, which has the aim to realize use hybrid workflow to realize a unified convergent platform for cloud, HPC, and big data, in particular for artificial intelligence. So first step was realize a hybrid workflow model, allowing people to describe their applications in terms of what they have to do and where each part must be deployed. Cloud, HPC, Kubernetes, VM, bare metal, SSH. And these hybrid workflows are orchestrated by Streamflow. Streamflow is a research product that is pretty mature now. It is a workflow management system able to basically deal in an automated way with our hybrid workflows. So what the user does is expresses application as a modular composition in which each piece needs outputs from previous pieces to start, and for each piece specify the underlying execution architecture in which he wants this piece to be executed. Then all the aspects like data transfers, fault tolerance, scheduling are dealt automatically by the library. And the new point of this platform is it can deal with multi-container environments for each step, so I can have a Spark cluster deployed on time, on demand, that executes my step and then is destroyed. And we do not pretend to have shared data spaces. Then we basically integrated Streamflow inside the OpenDeepHealth platform, which is the one I showed before. It was the blue square. And we basically coupled this Streamflow, which is developed by us, with existing external platforms that deal with all other aspects. We have authentication of the users, done with Keycloak. We have the authorization layer and the multi-tenancy layer that is realized with Capsule, that is the library that I will describe. And then the workflow execution layer is managed by Streamflow, which can execute either on cloud or on HPC. This is direct Kubernetes access. So people basically connect to kubectl, schedule their workflows, deploy their services, which are basically Streamflow descriptions of workflows, and collect the results directly from the cluster. This is the hard way to do it. This is unfeasible for physicians. Sorry. So we realized another access path, which is based on Jupyter notebooks. Jupyter notebooks are widely used by data scientists for prototyping, but they do not scale, at least not in their natural form, because execution is sequential. Communication protocol is bidirectional, based on 0MQ. So basically, you cannot put a Jupyter notebook executor on HPC because often HPC nodes do not have external internet connection. And they do not support multi-tenancy, or better, Jupyter Hub support multi-tenancy, but only very roughly. This is not enough for our use case. So what we did is instead of using the Streamflow coordination language, which is a declarative but is a programming language, so it's a bit hard for non-IT people to use, why we don't use Jupyter notebooks to describe workflows? And so we basically built a workflow description language using the metadata of the notebook. So it is JSON, basically. But since notebook of user interface, The user basically can program its workflow directly by clicking on buttons and declaratively telling each cell of the notebook where it must be executed, which are its dependencies, which are its requirements, and then the underlying runtime transforms the entire notebook into a distributed workflow. And also, it can deal automatically with other aspects like custom serialization, fault tolerance, background execution of cells. Will be clearer in a moment. The name of this library is Jupyter Workflows. It is based on Streamflow, so again, the library I described before. And what it does is basically start from code cells on your notebook, automatically extract the dependencies of each cell to build basically a direct cyclic graph of execution for the notebook, and then inject the concurrency inside the notebook. So if you execute an entire notebook from beginning to end, it will execute in parallel every cell that does not depend from its predecessors. So this is basically a workflow. But this is described in a very high-level way, in a very intuitive way for people that know how to use Jupyter notebooks. And also you have the possibility to build interactive workflows. So you can build one piece after the other, but each piece can scale on HPC, on multiple cloud instances, wherever you want. The big problem of this thing is serialization. We use Cloud Pickle, which is an extension of Python Pickle library to serialize objects. It can serialize almost everything, not everything. This is why we need the custom serialization logic by the users. This is basically the interface. So for each cell, you can specify input dependencies, output dependencies. You can specify parallel patterns like scatter gather to have parallel execution of the same cell. For example, when you have a list, you can process one element separately from the others in parallel. You can serialize in a custom way. You can execute in background, so you can basically use one cell to instantiate a server, start it, and use the other cells to instantiate the clients. And then when they will terminate, they will populate the output of the notebook as normal cells. So you can have basically description of a complex experiment inside a single document that is also ready to scale. And this is what that high-end user interface translates into when you press buttons, basically. So this is the cell metadata. They are sent to the executor. The executor knows what you want, knows the parallel pattern, the distributed pattern you desire for that execution, and orchestrates the execution of the workflow. Now, this is very good to hide complexities, but what about data privacy? Kubernetes is not so ready for data privacy because data volumes are stored at cluster level, and the unique way in which you can prevent access is to reserve them in a namespace so that other namespaces cannot create another attachment to that volume, what is called a persistent volume claim, basically. So, solution we adopted in order to remain inside Kubernetes, which is not the optimal one, but is the optimal with Kubernetes, is to have one dataset, so one tenant, one namespace. But this is not enough. Why? Because maybe you have an entity that brings multiple data. Maybe you have multiple users that want to use the data, but don't want them to stick with the same namespace. Maybe the way you assign resources, hardware resources to entities is not the same way you assign security. So you want basically to aggregate some aspects of multi-tenancy, especially management aspects, and separate them from the stick with the namespace way of reasoning. Because, for example, if one single entity brings 10 datasets, you don't want to assign a precise amount of resources for each dataset. You want to say you have 10 datasets, you have 4,000 core, use them however you want, but you still want to isolate the data. This is why we came with this solution, which is mapping one tenant to multiple namespaces, but still separating management aspects of different tenants at the central level, at the level of Kubernetes CRDs. So, Jupyter Workflow, high distribution complexity. Namespace, restricted access. Tenant are used for accounting of resources, but how these tenants can be injected inside Kubernetes. Kubernetes does not come with concept of tenant. Not raw Kubernetes, but Dario now will explain how this is possible, thanks to Capsule.
Well, too long didn't read Capsule is a solution. Just joking, it's not a pitch about Capsule. So it was really interesting because keep in mind that before proceeding, I think that we have to try to make it more interactive. So how many of you know what is Kubernetes? Raise your hand, okay? And how many of you doesn't know what is Kubernetes? Exactly, okay? Just me? Okay, some people. Okay, I'll try to explain you. So Kubernetes is great. We all know that it's a sort of standard de facto. Sorry if I use so many Latin words because I'm Italian, so it's pretty common for us. And Kubernetes is great, but got some limitations. So in the past, creating a Kubernetes cluster was a pain, and now, thanks to the interest by the community and all the developers, creating a Kubernetes cluster is easy peasy. You can spawn it in a few minutes using cluster kubeadm or cluster CTL if you're using cluster API. And it means that essentially, if you would like to achieve multi-tenancy with Kubernetes, the solution, according to the community, is creating several Kubernetes clusters. And I've been an SRE. I did the site reliability engineering for production clusters, and everything is easy when you got just a single production cluster, and things are getting worse and worse and worse when you're adding more production clusters. So what we did with Capsule, so essentially we decided to create an operator. So what is an operator? An operator is a binary running inside your Kubernetes cluster that is listening to events. So when a pod is going to be created, when a namespace is going to be created, and blah, blah, blah. And this operator is leveraging the Kubernetes capabilities. How doing that? Using custom resource definitions, CRDs. So essentially keep in mind that the Kubernetes API server is a big OpenAPI v3 specification server, and there is the CRD object that allows you to extend the API server with your own type. And that's great if you think about that, because in the end, it's a sort of dynamic web server where you can create whatever you want. You don't have to recompile Kubernetes. And I think that's the reason why the battle of container orchestrators have been won by Kubernetes, and that's great. And I would say that although writing an operator is really complicated, we try to make it as much as simple as possible. So I'd say that maybe I have to ask you, but Capsule is so hard to use. No. I don't think so. Thank you so much. Just joking. But our reason was to provide the same developer experience addressing multi-tenancy to the developers. You know, because I don't want to talk bad about other products like OpenShift or whatever it is. But, you know, with OpenShift is the Kubernetes distribution offered by Red Hat. You have to use their CLI. Instead, with Capsule, you got multi-tenancy, and you just need to use kubectl and do whatever you want. And this is really important. It's open source, so you can use it. We are eager to get feature requests, and we are trying to address everything. In fact, we had several discussions also on GitHub regarding some features to implement. And you know, it's open source. We would like to get more involvement from the community, and we are trying to do that. Anyway. Just to introduce you how it works. So Capsule, essentially keep in mind that when you're building a platform on Kubernetes, obviously you're going to have users, but users are not a concept in Kubernetes. Well, yes, but actually no. It means that if you issue kubectl get users, that resource doesn't exist. So how can I set authentication in Kubernetes? You have to use the API server parameters regarding the OIDC server and blah, blah, blah. So setting up the identity provider. So Capsule, since its goal is to provide a multi-tenancy, requires that you set up the authentication. Capsule actually can work with JWT tokens that are provided by identity provider, can use also the certificates, although you shouldn't use certificates in production clusters because they are really hard to manage in the long term. Anyway, the first piece for multi-tenancy is to set up the authentication, so the user. And then we are playing a lot with dynamic admission controllers. Who doesn't know what is a webhook? Everybody knows webhook, so we can talk in deep. So keep in mind that with Kubernetes, it's great because you can extend its capabilities with CRDs, but you can change also the behavior of Kubernetes. So how can I stop a pod from running with a certain container image? You have to use the dynamic admission control. So essentially, I'm going to explain you all the webhooks that we got. But with multi-tenancy, it means that we are building a platform, so you have to stop certain actions. For example, I don't want that Jupyter notebook, no, it's Jupyter, sorry, Jupyter notebook can spawn more than how many GPUs? Give me a number. 5 GPUs?
16.
16
At least,
GPUs,
deep learning.
Okay. Something like that, okay. You have to create a policy to do that. So you have to enforce some set of rules. And this kind of rules must be implemented in the dynamic admission control. But obviously, creating a platform, it means that you have also to take care of the resources. So what happens when we are onboarding a tenant? Pretty easy, because in the end, you are just creating a bunch of resources. They are creating namespaces, they are creating deployments, services, and blah, blah, blah. What happens instead if you would like to do the offboarding, so deleting everything? To achieve that, we are creating an owner reference from the tenant, so our Unix CRD to manage the collection of namespaces and the underlying namespaces. So if you would like to say, okay, this tenant completed everything, we have to prune everything, so garbage collector, all the stuff, you just need to delete this tenant, and thanks to the owner reference, all the namespaces are going to be deleted. Obviously, you can prevent that if you would like to get lost a bunch of information like, I don't know, persistent volume claims, and so on and so forth, but it's out of the scope. Just to say that you onboard the tenant users, and you can also delete everything with a single operation. So delete the tenant. Anyway, I would like also to provide what is a tenant, because we started talking about tenant, Kubernetes, but maybe it's much better trying to explain. So what is a tenant in Kubernetes? Because it's something that doesn't exist in Kubernetes. You got the namespace and then the cluster. So we got several resources. A pod is a collection of containers, and these containers are running in a namespace. And you have to think to namespaces like a sort of virtual cluster, although they are not virtual cluster. You are just creating an abstraction where you can run your applications. So that's great because we got this level, but we got also some other resources like the volumes, like the nodes that are cluster scope. So it means that the tenant cannot access them, okay? So the tenant in Kubernetes is a collection of namespaces. And as also Jacopo said, sometimes namespaces are not enough. And in the past, the solution, and I guess it's still valid, it also depends on your use case, is to create another cluster. So one cluster for a tenant, another for another tenant, and so on and so forth. And this could be cumbersome because I really love this representation because you have to find the perfect balance between cost efficiency and operational risk. Why this? Because having small clusters could be really cool because in the end, you don't have a single point of failure, but having a huge cluster can lead to a single point of failure, although it's much more simple because you just get a single entry point to do your stuff. So with the multi-tenancy offered by Capsule, we are saying, don't be too much small, don't be too much big, find your perfect balance. That will be a perfect meme, by the way, so with Thanos perfectly balanced, but I just wanted to be as much as possible serious. Anyway, this is Capsule, so I would like to provide you all the missing pieces. So how to identify a user? So essentially, it's pretty straightforward. We got the kubectl client that is connecting to the OIDC provider. There is the Kubernetes API server that is saying, okay, this token is valid, this is your token, and you can do whatever you want. And this is the JSON of the content of the token. So we can retrieve everything. In this case, this is just a service account. In Kubernetes, you can have several users. You can have the real users and then the service accounts. So the service accounts are robot accounts. You can use the service accounts to let your application to interact with the Kubernetes API server. Why users are so important? Because we got our back, because otherwise everybody could delete all the nodes, spawn several deployments with a lot of replicas and blah, blah, blah. So users are mandatory for RBAC, and RBAC are mandatory for multi-tenancy. But if you remember, I told you that also the dynamic admission controllers are really important. So this is the life of a request in Kubernetes. So we got our API request that will be handled by the HTTP handler in Kubernetes, where we got the authentication, the authorization, and then we got two kinds of webhooks. You can see we got the mutating and the validating. Let's start from the simplest one. So from the validating. Validating says, hey, I'm Dario, nice to meet you, and I would like to deploy Nginx, HProxy, or whatever container image in this namespace. Can I do that or not? And obviously, Kubernetes is not aware of my multi-tenancy environment. It's not aware if I can run untrusted images downloaded from Docker Hub or running using the host path mount. So with the webhook, you can create a set of rules that are saying this pod or this resource can be deleted, created, or updated. How can you do that? Well, Capsule is a sort of framework. So it could be a product, and actually is a product, but we are really happy because we are seeing a lot of people that is using Capsule, like Jacopo and University of Torino, to create software as a service, or rather platform as a service, leveraging the Kubernetes capabilities. So defining their use cases, they can create all these policies that will be enforced across all the tenants. So they don't have, every time they are onboarding a new tenant, say, okay, but I have to install this, I have to do this, and blah, blah, blah. All the rules are enforced from the cluster to the tenant. So can I launch this deployment? Yes or no? And finally, we got also the mutating webhook, because with the mutating webhook, we are able to create the connection from the namespace to the tenant. So we are creating the boundary and the relationship from the tenant to the namespace. And why using Capsule? Because it's so cool, I would say. No, that's not the reason. Well, maybe yes, I don't know. But it's a framework. So it means that it's not opinionated. I worked with several companies running platform as a service, not in the machine learning, AI, but rather working in the bank sector, and so on and so forth. And what I saw there is that developers are struggling to interact with a non-compliant Kubernetes API. Because in the end, what you would like to get is to say, I read the Kubernetes documentation and I don't want to read another documentation for another product. I want to use Kubernetes as it will be vanilla Kubernetes, okay? And with Capsule, you can build whatever you want as a service instead of Kubernetes, thanks to the multi-tenancy. And I'm referring to the infrastructure level multi-tenancy. If your application is implementing multi-tenancy like select orders, well, select asterisk from orders where user equals ID of the user, you're managing the tenancy at the application level, and that's cool. I'm not saying that you don't have to do that. But there are several kinds of multi-tenancy. And if you would like to sell a portion of your cluster to your business units, internal units, or external customers providing a separated infrastructure to avoid noisy neighbors and so on and so forth, you can do that using Capsule, as Jacopo is doing at the university. And finally, it's YAML. We all love YAML, right? No? No, I don't love YAML, but that's cool. But now I'll pass the word to Jacopo.
Thank you. So that was Capsule. Was really, in my opinion, easy to use because basically instead of spreading 1,000 actions around the cluster, you do it in a single place. But our problem is we have to deal with Jupyter notebooks. So why we need Capsule? Well, the problem of standard Jupyter notebooks is that they don't scale. So we make them scale. But the point is, I would want them to scale everywhere. I want them to scale where the people paid to scale. So basically what we do is assign resources to each tenant and use Jupyter Notebooks scheduler to spawn servers on that resources. How we do this? With Dossier. Dossier is a multi-tenant Jupyter as a service platform that starts from Jupyter Hub, but in introducing this cross-namespace multi-tenancy idea. And also, it integrates with other platforms to provide integration with many services from a single place. So, from the tenant CRD, which comes from Capsule, you configure the tenant rights. So, what resource you can use, how many namespace you are allowed to use, how many notebooks can you spawn concurrently. Then, from the same place, from the Kubernetes CRDs, you configure all OpenID Connect based authentication, so that if you want to enforce tenancy, you have to know the tenant of a user. This is a key point. So you have a mechanism to authenticate people, and this is done with Keycloak. And then Argo Workflow is used basically to insert loosely coupled integration among different pieces of the platform. So I will do one action. I always have to do the other action. So I make Argo to react to my first action and doing all the work in cascading, basically. So here I prepared some slides with the control flow, but they are too complex. I don't want to talk about them. No, not interesting. Let's come to the interesting part. So, recapping. When you have to build a platform for data scientists, basically you have two problems. One is the data, other is the scientist. So, for the data, you have many problems that are not how to deal with them in terms of learning. This is a huge problem, but this is more a research problem. The real problem is how to deal with data without violating rights, without moving the data when you cannot move the data, how to scale to higher and higher amounts of data to improve your prototypes. These are our solution, that is our view. We do not pretend to be the new way of doing data science. No, this is one proposal. But basically, this proposal solves the problem of the data by saying, okay, you want to bring the data, I give you multi-tenancy. So other people that bring the data cannot see your data. You have to trust me that I manage your data. You don't trust me? Okay. So use the platform and schedule the execution on your platform where the data are. And then use the cloud only to view the results, to combine them. For example, like federated learning workloads. You schedule your workloads on remote resources, train the models, aggregate on the cloud, and see the results. Other problem is the scientist, I suppose, saying, because you cannot ask a data scientist, which is very, very, very prepared on all the statistical aspects, learning aspects, and engineering aspects of maybe deep learning models to learn Kubernetes, which is not at least difficult enough, basically. So what is the solution? Hide the complexity behind what they know, behind Jupyter notebooks. Write your prototype, mark a cell as distributed cell, schedule the cell on HPC facility. Build a pipeline, data science pipeline interactively as a declarative notebook. Then mark the cells with input dependencies and treat them as overflows, spawning one on the cloud, one on HPC, one on cloud and HPC together, how you want. This is all hidden behind a single platform, which is complex, but is a single platform, which is called OpenDeepHealth. And this was the aim of the DeepHealth project, basically. So this is, again, the architecture. I think after all our words, this should be a bit clearer, but a bit. But the point is, this is based on separation of concern. You have many applications doing their job. They are basically interacting to each other. But the problem of microservice-based architectures is that microservices are many. Microservices are often out of your control because maybe they are spawned by the user of the platform. So what you need is centralizing the orchestration of the distributed platform. And this is the direction in which both Capsule with multi-tenancy and Dossier with multi-tenant Jupyter workflows want to follow. So have a single entry point in which you can access very different execution environments, like HPC, which is also which is normally accessed to SSH, or Kubernetes itself, which is accessed to kubectl. No, you access all from Jupyter. You don't want to use Jupyter? Okay, there is the hard way. kubectl and Streamflow CRDs, and the orchestrator workflows. To conclude, this was OpenDeepHealth. What OpenDeepHealth did in these 3 years, it has been used to, it has been hosted into the University of Torino cloud, which is called HPC for AI. It provided computing power with 16 GPUs and 192 cores, so it is a prototyping platform, but this is research. But it is scalable because it is based on Kubernetes, so you can transfer it to a Kubernetes inside a different cloud provider, and it can also spawn remote executions to HPC facilities. In particular, we use the Barcelona Centro Nacional de Computación, which is a huge HPC center with GPUs, high-end GPUs, NVIDIA Tesla V100, for example, that are the hardware you need to do machine learning, deep learning, basically. We gave access to 5 partners, so 5 tenants, basically, that use bring all 8 datasets for 6 use cases. So, as you see, we have 5 tenants, 8 datasets, some are grouped. We hosted a winter school with over 50 attendees. Another multi-tenancy example. We don't want the students of winter school to access medical data from people around Europe. And we will release the entire OpenDeepHealth platform as open source under the LGPL v3 license at the end of the project. Also, other platforms are open source. Streamflow and Jupyter Workflow, the orange one and the blue one are open source, LGPL3. These are the links you can also find in the slides that probably will be provided to you by the organizers, I think. Capsule is also open source, hosted on GitHub. Dossier is open source, so if you want to try, contribute, do whatever you want, please do. These are final links for the projects, European projects, and for the Classics company, and the cloud from University of Torino. And this concludes the presentation. So, open to questions. Thank you.
Thank you.
Claro.
Thank you so much. Is there any questions? That's the moment.
The difference between Capsule and dossier, if I understood correctly, a Capsule is providing multi-tenancy that is then used by dossier to distribute the workloads, right?
Yes, basically, with Capsule, you segment Kubernetes resources, assigning this amount of cores, this amount of software resources like pods, deployments, everything, to people and do the accounting part. So you can assign resources to an entity. Jupyter notebooks are used by people to run computation, basically. Jupyter Hub, which is the tenancy-aware version of Jupyter, can reserve one namespace for each user that you want to spawn a notebook and do computation, basically. This is not enough when you decouple tenancy from namespace. So what we did is rely on Capsule to make tenants and say Jupyter Hub to recognize the tenant of a user. So I am Jacopo, I belong to tenant 1. When I request a notebook to do computation, the notebook is spawned into my assigned resources. And if I want to distribute, all the kernels are spawned inside my assigned resources. This is the difference. So Dossier is Jupyter Hub built up on Capsule, basically.
So also because in the end, otherwise, you would end up creating several clusters for each tenant, and will be a nightmare, an operational nightmare from that perspective. Yeah, for sure, because if you have to create a different Kubernetes cluster for each tenant, you lose the centralization part that I said before. So you can scale even all over the world. But if you have one control plane for each working plane, you become mad the day after, basically. Think about updates, maintenance. I have to create another tenant where I want to put it. I have to change the resource assigned to one tenant. And also I have a much overhead because these are 5-6 customers, no more than that. But if you have 50, 500, and you have the whole control plane, which is also the OpenStack control plane, then the Kubernetes control plane, then the HPC control plane, it will be very, very hard to follow and very heavy also. Especially also considering the bootstrap time and the provisioning time, because although those are virtual machines, they are machines. So not Dockers. So you're welcome.
So another big clap for us.
Thank you very much.